Hey guys, it's Spiral Review for Spiral 20. To start off, we're going to look at our rational expressions section. First things first, I might notice that I have some stuff I need to factor. It's really limited to that middle guy, and you might expect, and you'd be right, that it factors to the two stuff on the ends. So in fact, this is going to be x plus 3 over x plus 4. I'm going to leave a nice space there. Minus x over x plus 4, x plus 1. Minus, and I'm going to leave some space here, x minus 1 over x plus 1. Okay, I'm going to look here. We've got x plus 4. We've got x plus 4. We do not have x plus 4, so you need an x plus 4. You need an x plus 4. Next one we've got an x plus 1 and an x plus 1. My first guy needs an x plus 1, so that all denominators become the same. I don't know why I put an extra parentheses there. Let's do some multiplying out. So we get x squared plus 4x plus 3. That's for that. Minus x. And then minus, that's going to be x squared plus 3x minus 4. And on the bottom, that's going to be x plus 4, x plus 1. I'm going to simplify the top if at all possible. X squared minus x squared, those cancel. 4x minus x minus 3x, oh, those also cancel. Okay. And then 3 minus negative 4 is going to be 7. 7 over x plus 4, x plus 1. And if you said, Mr. Carlson, wait, you didn't find any excluded values. You're right, I didn't. That should have been done way earlier than this, but that's x equals negative 4 and x equals negative 1. Those are my excluded values. On to number 2. First things first, we're going to do some factoring. This is going to factor into 3, 4x squared minus 1, which further factors into 3, 2x plus 1, 2x minus 1 for difference of two squares. The bottom of this is going to factor into things that multiply at 20 and add up to 9, 5, and 4. So we're going to have a 5x and a 2x. That's going to be plus 2 plus 1. Divide, which means I'm going to do some dividing, do some more factoring. This is going to be 2x and x. It's going to be minus 1 and plus 4. Now on the bottom, we're going to have 5x and x. And that's going to be a minus 1 and a plus 2. Next things next, I'm going to do my first round of exclude values. Can't use x equals negative 2/5. Can't use x equals negative 1/2. Oh, 2/5 happens again. Can't use x equals 1. Now I'm going to do some flippy. By the way, I also noticed that those are going to cancel out, so I might cancel those now and not have to rewrite. So we get 3, 2x minus 1 over 5x plus 2 times 5x plus 2 x minus 1 over 2x minus 1 x plus 4. And you might notice that that adds some additional excluded values. We can no longer have x equals 1/2 or x equals negative 4. We have 5 excluded values for this one. This is fun. Cancel, cancel. Cancel, cancel. And we're left with 3, x minus 1 on top, and x plus 4 on the bottom. Bada bing. Oh, look, that's it for this page. Next one, we've got to make all the denominators the same. Woo! I'm going to rewrite this as 3 over x plus 2. Leave a bunch of space. Minus 1 over x. Leave a bunch of space. Equals 1 over 5x. And leave a bunch of space. Okay, so carrying forward. I've got an x plus 2. There's no x plus 2 here, so that needs 1. We add that to the top and the bottom. And then I've got an x plus 2 that I need on the top and the bottom here. It's interesting because both of these problems appear to be the same problem. That's fun, unexpected, but that means I only have to do one problem in the review, so woohoo! Next, I'm going to check I've got an x. This one does not have an x. And this one does have an x. Woo, that's nice. And then finally, I've got a 5. This one does not have a 5. And this one does not have a 5. And now it looks like we have everything all together. So that's going to be 15x over x plus 2 times x times 5. This is going to be minus 5x plus 2 over x times x plus 2 times 5. And then this is going to be equals 1x plus 2 over 5x times x plus 2. All denominators are the same. If I multiply the whole thing by the denominator, those just go away, leaving me with 15x minus 5x plus, ooh, I gotta be careful, plus 10. I'll keep that in parentheses for a minute. And then equals x plus 2. 15x minus 5x minus 10 is equal to x plus 2. Combining some like terms, we get 10x minus another x is 9x. 2 plus 10 is going to be 12. That means that x is going to be 4/3, or 12/9. Let's see if there's anything else to do here. Woo, there's not. That's fun. I really should plug that in and check for an extraneous solution. But if I think about, again, I did not do my excluded values. Mr. Carlson, this is the worst. X cannot equal -2, and x cannot equal 0. If it doesn't fall into either of those categories, I'm probably okay. But plugging that in would be a better way to decide that. Sequences and series. We've got to find the sums of some series, and then we're going to have to find some rules. Okay, going from first term to fifth term of this series, we've got 3 times 1 squared plus 2, 3 times 2 squared plus 2, 3 times 3 squared plus 2, 3 times 4 squared plus 2, and 3 times 5 squared plus 2. In other words, 5, 11, 3 times 9 is 27, 29, 3 times 4 squared is going to be 48, plus 2 is 50, and 3 times 25 is going to be 75, plus 2 is 77. When I add those up, we get 77, 127, 147, 156, 166, 167, and 172.
Would a custodian please dial 2200? Thank you.
For number 8, we're looking at a similar thing, but we've got to go from 1 to 5 and plug them into this series, or this sequence. So it's going to be 1 plus 1 over 1, which is 2. That's going to be 2 plus 1 over 2, which is 3/2. It's going to be 3 plus 1 over 3, or 4/3. It's going to be 4 plus 1 over 4, or 5/4. It's going to be 5 plus 1 over 5, or 6/5. And looking at this, we're dealing with 2 plus 3/2 plus 4/3 plus 5/4 plus 6/5. The common denominator for all of those is going to be 60. So that would be 120 over 60 plus 90 over 60 plus 80 over 60 plus 75 over 60 plus 72 over 60. And then when I add all these things up, 120 plus 90 is 210 plus 80 is 290. Plus 75 is going to be 365, plus 72 is going to be 437. So 437 over 60 is our final answer. For number 9, if you're feeling adventurous, we might try to use our arithmetic formula. This is an arithmetic sequence. And in that case, we're looking at first term plus last term divided by 2, multiplied by the number of terms, which in this case, first term is going to be negative 5. My last term, I want the fourth term, so if I plug that in, negative 5 plus 3 times 3 would be positive 4, divided by 2 times 4 terms. Negative 5 plus 4 is negative 1. Times 4 is going to be negative 4 divided by 2. Should be negative 2. For number 10, rather than do these all out, I might just set up some sum formula. So the partial sum, that's fun, of the first 8 terms is going to be the first term, and that's going to be 1 minus r to the n over 1 minus r. This is awkward, but it's a little bit faster than having to do all these out like we did for the previous 3 problems. So this is my first term. So we're going to have my first 8 terms are going to add to 4, 1 minus, and that's going to be minus a half to the 8 over 1 minus a half to the 8th is going to be 0.99609. I'm going to multiply that by 4 and then divide that by a half to get 7.96875. Same thing for this lovely infinite one. I'm going to use my infinite formula. And I'm going to start out by looking at my r value, because I know I can only use this if r is less than 1. And 3 over 2, when compared to 1, is greater than 1. I can't use this. This diverges. There is no value, or you can call this an infinite value, for getting an answer for this if you'd like to. Okay. For number 4, the first of the number 4s, we've got to write the next 2 terms of the sequence, then write a general rule. A general rule is going to be a sub n, and that's going to be something that we're going to use an explicit formula, not a recursive, for this problem. I'm going to look here, and the first thing I look is, what am I adding? Plus 6, and oh good, that works for both of those. So this is arithmetic. We know that's going to be my nth term is the first term plus the common difference times n minus 1. That's the shortest way to write this. In other words, a sub n is equal to 4 plus 6 times n minus 1. For the second problem, number 4, we're doing the same thing, and now I'm going to look at what's going on here. First thing I'll check is, okay, we're going down minus 7 and then minus 19. Definitely not arithmetic. Okay, that's times 8. And then that's times, definitely not geometric. For something like this where I'm not really sure what the rule is, sometimes it helps to make a table where I write the term number, and then what I try to do is see if I can find any way to relate my term number to what's happening here. So is there a way I can get from 1 to negative 1, and then from 2 to negative 8, and then 3 to negative 27, and then 4 to negative 64? Multiplying and adding don't work. What about powers? Well, 1 negative, maybe one, like negative 1 squared. That give me negative 1. Negative 1, or negative 2 squared is negative 4. Okay, that doesn't work. What about third power? Negative 1 cubed, that's negative 1. Negative 2 cubed is negative 8. Negative 3 cubed is negative 27. Oh, look, I found my rule. So if this is n, this is going to be negative n to the third power. So my rule would be a sub n is equal to negative n to the third power. I also didn't write my next two terms for the upper sequence, which would be 22 and 28. Okie dokie. Moving on, we've got to find a general rule for the sequence below, and then find the eighth term. I think I skipped one. Oh, maybe not. Nope. So I'm going to look at what's going on here. That's plus 2.5. And then plus, oh, that's not 2.5 again. So this is not arithmetic. That's times 1.5. And I would bet my bottom dollar that this is also times 1.5. So that means that my common ratio is 1.5. My first term is going to be 5. My general term for a geometric sequence is the first term multiplied by a common ratio to the n minus 1 power. So we're looking at a sub n is equal to 5 times 1.5 to the n minus 1, and you are donezo. Zoom out. Next up, we've got some graphing. I also added some domain and range things. I'd like to point out some of the things that we have to be careful of with graphing. First things first, we got to choose x values that make our exponent nice numbers to make our lives easier. In this case, just an x. So let's do negative 1, 0, and 1. Second of all, we know that my horizontal asymptote is plus whatever is at the end. In this case, it's going to be 0. So first thing I'm going to do is identify a horizontal asymptote at 0. Plugging in some values, we get for negative 1, 1/3 times 3 to the negative 1 equals 1/3 times 1/3, or 1/9. That's going to be really close to the x-axis. Okay? 1/3 times 3 to the 0 is equal to 1/3 times 1, or just 1/3. And that's way above what it actually should be. That's fine. I might zoom in so I can see this better. There we go. That's supposed to be 1/9. Negative 1, 1/9. And 0, 1/3. It's nice to write points in so we can see them. And then finally we've got 1. Okay. So it's 1/3 times 3 to the 1. 1/3 times 3 is just 1. Okay, that's pretty cool. So there's the point 1, 1. The graph is going to look like this with a nice slow build up to an exponential curve. Let's talk domain and range. For the domain, I know my graph is going off both sides of my page. You might also think about this, that there are no numbers that we can plug in that would screw this up. My domain is all real numbers. We're not going to be able to see that when I zoom out, so I'm going to rewrite that here. All real numbers is the domain. In fact, for all exponential equations, all real numbers will be the domain. That's a pro tip. Second thing is going to be the range. The parts of my graph that show up here are only when y is greater than, not even equal to, when y is greater than 0. You might notice that's based on my horizontal asymptote. This thing sits on top of it. It's never going to go below it. So my range is going to be based on that. In a couple weeks, we're going to look at the inverse of these functions, and you might see a similar pattern, except with the domain and range flipped. For number 13, I'm doing the same thing. Again, I'm going to choose some points that make sense here. I want the top to be negative 1, 0, and 1. That means that for my exponent, x values of 0, 1, and 2 would make that true. Okay? Next thing I've got to do is identify my horizontal asymptote, and here I've got 0 again. Zooming in so I can see my graph. First things first, we're going to plug in 0. So we've got negative 2 times 2/3 to the 0 minus 1. Oh, that's just negative 1. So negative 2 times 3 over 2 is going to be negative 3. Then we're going to have negative 2 times 2/3. 1 minus 1 is 0. Negative 2 times, well, that's just 1. So negative 2. Cool. And then finally, we're going to have negative 2 times 2/3 to the 1. And that's going to be negative 4/3. Sometimes if you want a deeper gradation of this, if you want to see the numbers a little bit farther apart, you might choose numbers that are farther apart than 0, 1, and 2. And that would be okay. Again, these are just to find some nice and easy values for us to work with. So like 0, negative 3, 1, negative 2, and 2, 4/3. And I want to see a nice exponential curve heading towards that asymptote. And I'd love to see the equation for that asymptote. Do that in the last one? Nope, bad, Mr. Carlson. Okay, once again, we'll zoom out and talk about domain and range. Domain, I can plug in any number. That's hint number 1. Hint number 2 is that my graph is going off the grid in both directions, off the charts. So that's going to be all real numbers for the domain. For the range, this time we're below that line, so y is less than 0. Again, we don't touch it, so it's not less than or equal to, but we don't ever get to that point. We're always below it.